Here's a sort of philosophical question. What are the strengths and weaknesses of vectors? And I hope you look at that and your first response is, wait a minute, compared to what? If we ask to evaluate strengths and weaknesses of something, I guess that has to be in contrast to some alternative. If vectors are the only game in town, then what difference does it make what their strengths and weaknesses are? You have no choice but to use them. Well, really, the reason I'm asking is it turns out vectors are not the only game in town. But I'm actually getting at something more fundamental than that, which is, if we think about what we're using a vector for, maybe it doesn't match up with what a vector actually is. And we're getting to a point where we have to really focus on that distinction between what we use something for, what it does, and what it is underneath. And so we should ask the question, based on how we've been using vectors recently in this course, to the vector, what is it exactly that you're here to do? And I would argue that right now, the way we've been using vectors most of the time over the past few weeks has been as some general catch-all way to represent a sequence of values. And what do I mean by sequence? Well, I guess what I mean is the same sort of thing you'd use in math when you say the word sequence, which is a bunch of values. Now, unlike in math, we require our sequences in this context to be finite, so a finite number of values, in a particular order. And we also allow the same number to appear at multiple positions in the sequence. And if you think about it, I think a vector can do that job quite well. But is that what a vector really is? Can we say that a vector is just a mathematical sequence? Well, of course not. A vector represents that, or we can choose to use a vector to represent that. Deep down, a vector is something else. A vector is actually a wrapper around a sort of C-style array. And we like to think of a vector as sort of a generalized, idealized C-style array. But the way that we've been using a vector recently has been a representation of this sequence from math. Now, the reason why that's so significant is it turns out that there are other ways of representing a sequence. And before we talk about those, we do sort of have to untangle this word sequence from the word vector. If I can represent a sequence in more than one way, then when I talk about a bunch of values in a row, am I talking about a vector or am I talking about a sequence? And therefore, we've reached a point in the course where it's suddenly time to introduce some terminology. And you know that in general, I'm not a big fan of introducing new terminology if we can avoid it, but these two terms are really important. And also I should add, not that it makes much of a difference to you whenever it is you're watching this, but I'm actually recording this video on January 1st. And so, I don't know, new year, new me, I guess I better try and learn some new terminology this year. Let's start with this one, abstraction. The word abstraction is really, really important in computer science and really important in programming. It's important in a lot of disciplines, and actually, arguably, in any academic discipline, you're probably going to come upon some use of the word abstraction. I would argue that in day-to-day parlance, it's used a lot more often in computer science than a lot of disciplines. And what it refers to is the ability of computer scientists, which I think is a requirement these days in computer science, especially in programming, the ability of computer scientists to separate how something works internally with how we use it. So I want a sequence of values, and I choose to represent that sequence using something in C++ called a vector. And we could even argue that a sequence isn't the most general thing we might want to use. There are times, even in the past few weeks, when we've just wanted to store a bunch of numbers or a bunch of strings. We haven't cared about the exact order in which we store them. And so in that sense, a vector is a specific way to implement a sequence, and a sequence is a specific way to implement a collection, just a bunch of stuff. Whereas a collection just has a bunch of things, a sequence requires that those things be in an order that is kept significant to us. So us, the programmers, choose the order of the elements in the sequence. And even more specifically, a vector provides us a way of viewing a sequence through the lens of maybe an array. So in a similar way to arrays in C. The idea of abstraction is the ability to talk about a set of requirements in terms of a more general form. So for example, talking about keeping a collection of values and not worrying so much when we're talking about what we're trying to do with those values as far as how those values get represented internally. Do we use a vector? Do we use something else? We are abstracting the idea of a collection away from the underlying vector that represents it. We actually see this in a lot of other contexts too. It's hard for me to think of very many examples in real life, but one example would be if I put on the grocery list chips, all right, chips on the grocery list. When I actually get to the grocery store, what I'm really doing is saying, well, I want something crunchy and flavorful that I'll eat the whole bag of and probably regret eating. Now, given that it's New Year's, I guess I should think about whether I want to keep doing that in 2022. When you finally watch this video, come and ask me if I actually managed to give up eating chips. But I read the word chips on the grocery list, and obviously I've abstracted what I want. A snack item, a crunchy snack item, probably deep fried. I could come back from the store with tortilla chips or potato chips, and with any of various different flavors. All of those represent one specific snack item, but I've abstracted away sort of the overarching concept of I want chips. Another way that we use abstraction, a more computer science applicable way, is when we draw those diagrams, when I trace through programs. So here I have int x and int y. We of course have to understand, and I'm sure you all understood before CSE 111 was over, that internally a computer isn't a bunch of drawings of boxes. Obviously, that's not the way a computer works. A computer does represent data in a way that corresponds to this visualization. Now, the fact that I'm drawing it visually, that is not the abstraction. The abstraction is pulling out the fact that I'm storing data in variables. The variables have names, the variables have types, away from what's really going on in the computer, which is a bunch of zeros and ones stored in the computer's memory. I've abstracted the important concept away from what's really happening, because I don't want to talk in terms of transistors and chips and zeros and ones in memory. And maybe that gives you some impression as to why this is so important in computer science. Because when you think about it, deep down, the computer that you're using relies on low-level concepts from physics, like quantum physics, and things you might have heard of out of the domains of electrical engineering, like how transistors work and logic gates. When we talk about computer programs, so when I say read a bunch of strings from the user and tell me the longest word, I don't want to be thinking in terms of quantum physics and logic gates. I want to think at a higher level. And our ability to abstract is one of the reasons why we're able to do that at all. In fact, all of programming, so the existence of a programming language, is itself an abstraction. When I write lines of C++ code instead of zeros and ones or assembly language instructions, what I've done is abstracted the behavior away from the processor. So abstraction is a big deal. And by the same token, although I've written this list here as sort of a ladder going from vector as the least abstract thing up to collection as the most abstract thing, keep in mind that deep down a vector is doing something behind the scenes that we may not fully understand yet, which is a vector is using these C-style arrays, but providing us some, I guess you could say, magic functionality that gets rid of many of the disadvantages of a C-style array. So for example, in a C-style array, when the array fills up, you can't make it any bigger, whereas a vector seems to be able to grow and shrink as needed. And we're going to see more this week of ways of expanding and contracting vectors. So the word abstraction is a big deal. We're going to use it over and over again from now until the end of the course. It is a really big deal, and it's an even bigger deal going forward into later courses. Hand in hand with the word abstraction is this second piece of terminology, the word encapsulation. And generally speaking, a good abstraction, so being able to think about things in terms of a collection as opposed to specifically a vector, a good abstraction often goes hand in hand with good encapsulation. So in a nutshell, encapsulation is the ability of something to conceal what's happening below the surface, so that you interact with something in a convenient way without needing to understand how it works internally. And a vector is pretty well encapsulated. We might understand, I guess, intuitively that a vector might secretly be a C-style array deep down. But we don't use it that way. We call pushback, we call dot at, and when we call pushback, the vector magically grows in size. When we call dot at, we're able to access an index of the vector. It takes care of everything behind the scenes for us, so we don't. Now, we might understand intuitively maybe what's going on behind the scenes. The key thing with encapsulation is that we don't have to. And the other side of that is we're also not allowed to. I'm not allowed to break in and mess around with what's happening internally inside the vector. The vector is encapsulated. I'm not allowed to see inside, nor should I have to see inside. Other examples of encapsulation that you might encounter, I've used the example in this course of small appliances before. If you want to make toast, you can go to the store and buy a toaster. And then you put bread in the toaster and you press the thing down and then the toast gets made. So bread goes in, toast comes out. You might have some idea of what a toaster does internally, but you don't actually have to understand that to be able to use the toaster. But the other side of that is maybe you don't even need to. So maybe it should be impossible for you to know what's going on in the toaster. All you know is bread goes in, toast comes out. If somebody invents a more efficient toaster that doesn't use electricity, does that make any difference to you? I would say it doesn't. Even if you still plug it in, as long as you put bread in, push the thing down and you get toast, why does it matter whether it's using electricity or not? As long as you get toast when you're done, you have a toaster. And we'll see other examples of this later in the course. It turns out designing a good abstraction often involves designing effective encapsulation. So that is, the ability to use something without needing to understand what's going on inside of it is maybe more of an application of the word abstraction, whereas the inability for you to see what's happening inside of an object is an example of that object encapsulating its behavior, shielding you from its internal behavior. Those two concepts together in balance, abstraction on the one hand and encapsulation and on the other hand, allow us to organize our programs effectively, because we can then define different parts of our programs that sort of work with each other. But when I'm working on one particular part, I don't have to worry too much about what other parts are doing internally. Just what do I do to use those other parts? We've seen examples of abstraction and encapsulation going back to CSC 111, because when we write functions, we are engaging in abstraction and encapsulation. If I write a function to read a line of text from the user, well, that's an abstraction. I mean, what really is going on when I'm getting text from the user via the keyboard is actually several layers of abstraction. I call the function to get a line of text, and when it's done, I have a line of text. I view the operation of getting a line through the abstraction of this one function call. And on the other side of things, I don't need to understand how it's doing that behind the scenes. That's one way that the function call's behavior is encapsulated inside the function. However, the way we're going to use the word encapsulation later in this course, I think, is a much more obvious use of that term. So we'll begin looking at that this week, but it will really get exposed a lot more in the next few weeks of the course. For now, I want to talk about ways in which we can implement this abstraction of a collection of stuff without just using a vector. We've been using a vector so far mostly because since a vector has similarities to a C-style array, it might be the most natural and comfortable introduction to this idea. But it turns out there are lots of ways in the standard library that you can store a collection of things. In fact, there's even more than one way to store a sequence of things, a sequence being a more specific type of collection. Okay, so what are the strengths and weaknesses of a vector? So std vector allows us to treat, so the underlying thing that a vector purports to represent is sort of like an array. We can index it like an array. We know already that we can also add elements at the end very quickly. The process of adding elements at the end is non-trivial. I'll try and define that a little bit now, but we're going to come back to that later in the course. And a vector is a way of implementing the abstraction of a sequence. So I'm going to use the term programmer-defined ordering for that. That means if you define a vector and you add these elements in this order, they stay in this order. You get to decide, as the programmer using the vector, you get to decide the order of the elements. I don't want to call this user-defined, even though you are the one using the vector if you're programming it, because I don't want to bring the user of the program into this. So the end user that runs your program, they're not the one who defines the ordering of the vector. It's you, the programmer, calling the functions of the vector. Now, the vector actually also has weaknesses. Weaknesses that may not have been obvious so far, because I guess it's reasonable to argue that at this point in the course, we have sort of gone out of our way to showcase the strengths of the vector while we're using it. Part of the sales job of convincing you to use vectors in your programs. To get at the weaknesses, I want to talk a bit about what the vector is underneath. Now, this is sort of getting inside of that encapsulation, violating that encapsulation a bit. But it's good to have a conceptual model of what the vector is for the sake of discussing strengths and weaknesses. When you have more than one option of what to use to implement your sequence abstraction, it's worth knowing what the relative strengths and weaknesses of each option are. So deep down, a vector actually is stored in a C-style array. And the reason the vector appears to grow and shrink is that let's look at a vector, a smaller one here. Here's a vector that uses an internal array of size 3. And the question you should ask is, wait, if the vector is internally a C-style array, what happens when it's full? If I try and do push back on a vector with this internal array, how will the operation succeed? And the answer is, well, the vector uses a C-style array internally. C++ does support C-style arrays. The vector uses a C-style array and works around the difficulties with it getting full by just basically creating a new array when the array gets full. So if this vector got full, if I wanted to add a new element to this vector of size 3, it would make a new internal array, probably double the size. It would then copy all of the elements from its old array into the new one, and then delete the old one. And it would do all of this behind the scenes. As far as you're concerned, the vector was always this whole thing. It would also keep some empty space at the end of the array to reduce the chance that it fills up again in the near future. If I want to push back into this, I would just add to one of the empty spaces. If I ask this vector, what is your size, it would tell me its size is 4. It just keeps these empty spaces at the end secret. That way, if I want to add more elements, it can do that insertion apparently instantly. If I want to remove an element from the end, similarly, it just erases it and then leaves the empty space and pretends the size is now 4. That's one way in which it encapsulates what it's doing. From the outside, it appears as if the vector is always exactly as big as it says it is. But internally, encapsulated inside the vector, there are a bunch of empty spaces that the vector uses to avoid having to resize. However, when the internal array gets full, the vector does resize itself. It's hard to justify mathematically exactly how often that has to happen, but I'll suffice it to say for now, the vector is designed so that resize operations happen very rarely. So they don't happen very often, and therefore most push-back operations just amount to filling in one of these empty spaces. And so for that reason, we generally characterize a vector as having fast insertion and removal at the end. So at the end, we just use those empty spaces, assuming that resizes happen very rarely. Okay, but they do happen occasionally. Now, that said, I can also, it turns out, insert elements anywhere else I want in the vector. So we'll see in a future video, I think 2 videos from now, we'll talk about how do I insert an element not at the end, not push back, but how do I add an element right in the middle of a vector? How do I say, hey, insert the value 999 after index 1 of the vector? It turns out I can do that. And the vector will let me. There is an operation of the vector that is defined to do that for me. The problem is that's not fast. The vector, because it's meant to mimic a C-style array, has the same disadvantage, which is that all of the elements are contiguous. And therefore, if I want to insert something in the middle, the vector can do that for me, but it has to make space first. So if I want to add 999 to my sequence after the number 6, the way I would have to do it, the way the vector would do it internally is, it would just move everything over to make space. And then once the space is empty, it adds the element that I want. Notice that the sequence that's being stored internally is now the sequence with the element inserted. The problem is, to perform the very local operation of adding one element, I had to make a global change. I had to move over every single element of the vector after the insertion point. So inserting at the very beginning means I have to move over everything. On a vector that contains n elements, I have to do n operations to insert one value. If my vector has 1 billion items, I may have to move 1 billion things one position to the right. That's really slow. And although we don't generally care about speed, when we work with a lot of data, we might get vectors large enough where that speed disadvantage can be noticeable. And when there's a practical effect, I guess then it's reasonable to worry about the speed of operations. And so insertion and removal at the beginning or middle of the vector is therefore pretty slow, because if the vector gets large enough, moving all those elements can take a long time. I guess I should show off what happens if I remove at the middle too. Suppose I say, remove this element 17. Well, I mean, I can't just erase it and expect people to jump over the gap. Instead, I have to fill in, I have to shuffle everything back over to the left. So I end up with this. And then the vector if I ask the vector its size, it will say it now has size 6, even though secretly it's keeping some empty space at the end in case it needs it. So a vector, therefore, is not a good choice if I want to do a lot of insertions and removals at the beginning or middle of the sequence. And you'll observe in the examples we've done so far in this course, we haven't done that very often, partially because we've sort of engaged in a bit of bias towards vectors. We've had a lot of applications that vectors just are naturally good at. Another thing a vector is not very good at is searching. So if I want to ask the question, is the element 116 in this sequence? Well, I can answer that question using a vector. The way I would search the vector is just look at every element. And when I hit the number 116, I would say, oh yes, I guess it is in the sequence. But the problem is, if I ask for an element that isn't in the sequence, so if I say, does the sequence contain the value 0? Well, to know the answer to that, you have to look at every single element and then decide if it equals 0. And eventually you get to the end and you say, well, I guess no, the element 0 is not in this sequence. If the vector contains 1 billion elements, you have to look at 1 billion things to ask that one question. You have to look at 1 billion elements to answer yes or no, does the vector contain this thing? In the worst case where the thing isn't in there. And of course, looking at a billion elements is slow. But it turns out that that's just not one of the vector's strong points. We're going to see in a minute there is a collection we could use that is very good at searching, but we have to make some trade-offs. In general, you can't always get what you want. So the trick with the standard collections, of which vector is one, is to choose a collection that does the things you want and sort of optimizes the operations you need, and then maybe trade off by sacrificing some operations that you don't need. If you want to be able to index quickly, so because a vector is internally a C-style array, if I ask for index 3, it can fetch that index very quickly. If the vector has a billion things, I can ask for any index of the vector, and it's able just to jump immediately to the index that I want in one fell swoop. So in one operation, it can get me any index of the vector. We'll see that other collections don't necessarily have that advantage. A vector can insert quickly at the end and remove quickly from the end, and a vector gives me the sequence, so it gives me the ability to define my own ordering of elements. In exchange, searching is slow, and inserting and removing at the beginning and middle is slow. So what happens if we want to insert and remove at the beginning or middle, and we want that to be a fast operation, and we're willing to give something up in exchange? This is actually a question that I answered in 111 as well. So in 111, we eventually talked about, near the end of the course, what is the opposite of an array? So arrays have disadvantages. One of the disadvantages of an array is that they fill up. Now, a vector doesn't have that problem, although the resize operations can, in some cases, be a problem. But an array also has the difficulty of I can't splice elements in at arbitrary locations very easily. In 111, we had an alternative. The alternative was a data structure called a linked list. And just to remind you, I guess I'll use a separate slide. A linked list is, instead of one big contiguous block of storage with a bunch of elements all in a row, a linked list is a bunch of separate elements all sort of floating around in space. And we sort of visualize this as a bunch of boxes floating around. Often I talk about them floating in the ocean, I guess. And each of these, which is called, this is a node. Each node of the list contains maybe two pieces of information, and that would be an element, so the number 6, and directions for where I can find the next node. And I also keep one other special piece of information, which is a tether, sort of tethering this set of nodes floating at sea, tethering them to shore. And we usually call this a head pointer. If I want to know what sequence this list represents, I start at the head pointer and I follow the pointers all the way through the list. And I would get the sequence 6, 10, and 17. In this case, this is called a singly linked list because each node of the list contains directions to the next element. So I can walk forwards through the list, but I can't walk backwards. And if I wanted to add a new element to the list, so if I said something like, hey, insert the value 187 between the 10 and the 17, well, what I would do is make up a new node. There it is. I put the value 187 in it, and then I splice it in. So I sort of cut the link between the 10 and the 17, and I put the 187 between the two of them. All right, there we go. What's interesting to observe about this, what you probably recall from 111, is it makes no difference how many things were after the 17. There could be a billion elements after the 17, but to actually insert the 187, I do a very local operation. I just splice it in. All I need to know about is what comes before and what comes after. And so that gives me what I don't get with a vector, with an array. I'm allowed to splice elements in wherever I want, and by the same token, I can delete them. So if I want to delete the 187, I would just have the 10 redirect over here, and then I would splice this out. Again, a very local operation. I don't have to look at every other element of the sequence. I just have to modify the elements nearby where I'm making the modification. So that's one advantage of linked lists versus arrays. One disadvantage is I'm not allowed to ask for the element at a particular index with much convenience. I can still do it. I can say, give me the element at index 2. But the only way to know what's at index 2 is to start at the beginning and count it off. So there's index 0, there's index 1, there's index 2. At any given time, because the list can keep changing internally, the indices may not be consistent. So if I change what's in the list and I want to get index 2 now, I have to count it off again from the beginning, 0, 1, 2, because the list can change at any point, so I can't necessarily remember exactly what index belongs to what node after I've made a change. That means if at any given time I want to index into my linked list, I have to loop over it. So if the list has a billion things, I may have to loop over 1 billion things to know what occurs at a particular index. And that's one of the trade-offs that I have to make with data structures, is I'll choose a data structure that gives me some operations that are fast, in exchange making some other operations slow. So I have to choose a trade-off. And so there are some disadvantages to using a vector in C++. For example, I can't insert and remove at the beginning or middle very quickly. The standard library defines a whole bunch of other ways of implementing a collection. The abstraction of a collection can be implemented by more things than just a vector. So a vector gives us these strengths and weaknesses, but there's also a data structure called StdList. And internally, an StdList is in fact a linked list. So the linked list I've drawn here is what we call a doubly linked list. So each node contains directions to what comes after it and what comes before it. But like a singly linked list, modifications of a doubly linked list are all very local. I can insert a new element between any two existing elements just by redirecting a bunch of pointers between those two elements. So cutting the links between them and then reconfiguring some pointers. A very local modification. And so this provides a good counterpoint to the vector. It is still a sequence. If I am the programmer, I can define my own ordering of elements. So whatever order I insert them, that's the order they're in. And unlike a linked list in C, if I use StdList, I don't have to worry about the actual nodes and pointers flying around behind the scenes. We'll notice in the next video, I can just use push back on a list if I want to. In fact, there actually is also a function push front, because a list is so good at inserting at arbitrary locations, it provides us a shortcut to add elements anywhere I want. And we'll unpack that a bit once we get to the next video and the videos after that that actually work with code. So a list provides us a different set of strengths and weaknesses. I still get a programmer-defined ordering. I'm still representing a sequence of values. However, I get fast insertion and removal anywhere I want, not just at the end. The trade-off is indexing is now slow, because obviously I can't jump to a particular index because when I modify the list, all of the indices can change. So for example, at the moment, the indexing looks like this. So 116 appears at index 3. If I were to insert something here, then as you can tell, all of the indices suddenly change. So I can't keep track of all the indices as I go, because as I modify the list, the entire indexing scheme changes at each modification. I'm going to undo that though, because that looks sort of ugly. And just like a vector, a StdList also has slow searching. Because it's a sequence and it's in an arbitrary order, if I want to ask a question like, does the number 999 occur in the sequence, I just have to start at the beginning and keep walking until I find it. And so if the list has a billion things, I may have to look at a billion things in the worst case to answer the question, does this list contain a particular value? Okay, but already we've seen an example of two different ways to implement the abstraction of a sequence, each with their own strengths and weaknesses. And which one should I choose? Well, it depends on what I'm doing. Do I need fast insertion and removal at every location, or do I need fast indexing? I think that's the determining factor for vector versus list. But there are other things I might care about. So for example, both vector and list have slow searching. And in exchange, I get to define my own order of elements. But maybe I'm storing a bunch of pieces of data, not because I care about their order, but because I want to keep asking questions like, is this value in the collection? So one example would be, if I'm storing a bunch of data about students in the course, I might want to quickly ask questions like, what is the grade for this student? Or is this student in the course or not? Just search for them. I don't care so much what order the students are stored internally. I just want to ask questions about, is a student taking this course or not? And so the standard library defines more standard collections to optimize for different strengths and weaknesses. And the next one is StdSet. So StdSet isn't a sequence. It is a collection. I can store a bunch of values, but I do not get to define my own ordering. If I add a bunch of things to a set, the ordering that the set stores them in is not up to me. So I don't get to use push back or whatever like I would on a list or a vector. Instead, I add the elements, the set curates them itself, it does its own bookkeeping, it puts the elements into ascending order. So they're always in ascending order. In exchange, for me giving up the ability to order my own elements, I am able to search the set incredibly quickly. And we'll see an example. It is a huge contrast. Just to give you a sort of a point of reference, if I have a set with 1 billion items in it, actually we'll start with 1 million, just so the difference becomes even more stark. Actually, well, no, I'm getting ahead of myself. If I have a set with 1,000 things, So if I had a vector with 1,000 things and I wanted to ask a question, does this vector contain the number 6? Well, then I'd have to look at all 1,000 things in the worst case, all 1,000 of them. If I have a set with 1,000 things and I want to ask, does this set contain a particular value, the set will be able to look at most maybe 11 of those things. So I have 1,000 things. I can search them by looking at 11 of them. The set has a clever organization scheme that doesn't require looking at every element to do a search. 11 things out of 1,000. But it gets better. If I have a set with 1,000,000 things, then it will look at maybe 20 or 21 if I want to search it. If I want to ask the question, among these 1,000,000 items, is any of them the number 6? It'll look at about 20 of them to answer that question. And if I have a set with 1,000,000,000 things, it will look at about 30 or 31. That's it. And that's amazing compared to a vector where I would look at all 1,000,000,000 of it, all 1,000,000,000 elements in the sequence. And so, of course, a set is great if I want to do a lot of searches. I mean, it's amazing. You might have noticed that the growth rate, as I keep adding zeros, the number of things I have to search through seems to grow in a linear to the number of zeros, I guess. It turns out that as I increase the number of elements in the set, if the set has n elements, the search time is approximately, it's approximately log in base 2 of n. And we don't want to get too deep into this right now. We'll come back to this later. But suffice it to say, what you know about logarithms already is that a logarithm grows much slower than the value of n. And that means that as the set gets bigger and bigger, the search time doesn't grow very fast. And I'll just put in a plug here. There is an entire course that analyzes algorithms and data structures in terms of n and log n and things. It's CSE 225, a course that I used to teach a lot. Although these days I haven't taught it. I haven't taught it in a couple of years. So a set is great for searching. In exchange, though, you don't get to define your own ordering. Insertion and removal is still pretty fast. Not as fast as a list, but it's still pretty fast. It also is on the order of log n. And again, don't worry so much about the log n for today. We'll come back to that later. Okay, so what is a set internally? We know what a vector is internally. It's sort of an array. We know that a list internally is a linked list. What is a set internally? I'm actually not going to answer that. I am quite in an insolent turn, I'm going to refuse to answer that question for now. I actually like the idea that introducing a set this way forces us to view it as an abstraction. So we don't actually know what's going on behind the scenes. That's how well encapsulated it is. I promise I will tell you eventually what a set is internally. So a set maintains a bunch of elements. It forces them into ascending order. So if I add the number 116, the set will maintain it internally in a way that forces it to be there, I guess. Although a set is not just an array of values, and it's not just a linked list. It's something more complicated than that, because inserting into an array, if I have to keep them in sorted order, is slow. Inserting into a linked list in sorted order is also slow. The set manages to keep searching and insertion and removal fast. In exchange, when I iterate over a set, I will always see the elements in ascending order. I don't get to define my own order. Similarly, there's no indexing. I can't just ask for index 3, because since the set is rearranging my elements as I insert them, there doesn't really make much sense to allow indexing at all. So if I add the element 13, it goes here. If I had indexing, so if I index the set right now, this is 0, this is 1, this is 2, this is 3, this is 4. But if I add an element in the middle and it gets forced in ascending order to be there, then all of these indices are suddenly irrelevant. And so the set does not support indexing. If I want indexing, I have to use a vector. And I also have this extra requirement, which is that because the set needs to maintain its elements in ascending order, the element type has to have some way of ordering itself. And numbers and strings actually have this, and it turns out we can define this on our own for our own types, but some types don't have this, and there are some types where it makes no sense to try and order them, and you can store those types in a set. Okay, so a set has these trade-offs. We can search quickly, but we have to, compromise on some other factors. What if I'm willing to compromise on even more? So one, I guess it's listed as a weakness. The ordering is not programmer defined, but in this case, the set maintains ascending order, which actually might be sort of annoying to maintain if I were defining it myself. So a set gives us the benefit of ascending order. What if I were willing to sacrifice even that? So what if I were willing to say, hey, I just want fast searching and fast insertion removal. I do not care about anything else. I want to be able to search as quickly as possible. I don't care what order anything is stored in. I just want to search quickly. There's one more option. There actually are a few other standard collections we're going to talk about later, but there's one more option for today. StD unordered set. Unordered set has fast insertion and removal and extremely fast searching. So really it is optimizing searching at the expense of everything else. However, when I insert elements, they are not in a programmer-defined order. They are maintained in an order that is very opaque to us. The order is rational, so the unordered set is maintaining the elements in a way that makes sense to it internally, but it makes no sense to us from outside. As a result, just like a regular set, there is no indexing because the elements are maintained in a strange order that can change at any moment. And a little bit of extra machinery, a little bit above the scope of the course, but a little bit of extra machinery is required for the element type. About the same amount of extra machinery required to have a less than operator, but it's not a less than operator specifically. It's a special function that has to be defined. I might talk about that later in the course. Not in a video, though. It might just come up later in a lecture or something. But an unordered set gives us extremely fast searching. And again, I'm going to force us to view this through the lens of encapsulation. So what is an unordered set internally? Oh, I don't know. It's just a bunch of elements sort of floating around. If I iterate over this unordered set, it might give me back the elements like 17, 10, 187, 6. It just gives them back in some strange order. Now, it is keeping them internally in an order that makes sense to it, but we have no idea what it is. It's sacrificing everything in exchange for very fast searching. It can answer the question, is this element in the set, very quickly. What's interesting about the order of the unordered set, I guess I'm not done with that. What's interesting about the order of unordered sets is, if I go and add a new number to the set, so I add the number 225, and then I iterate over the set again, adding one element to my set could completely change the ordering of the elements when I iterate over it. I'll still get every element, but I may not get them in anything close to the same order they were in before. And that's because the unordered set internally is maintaining a very strange ordering just for the sake of being able to search quickly. And we'll talk about that in future videos, but of course, if I'm ever in a situation where all I care about is searching quickly, then I would use an unordered set. If I'm in a situation where I want some semblance of order, so for example, I'd like to maintain elements in ascending order, and I still want pretty fast searching, I might use a regular set. And there are a few cases where we might do that in this course. If I'm in a case where I would like to insert and remove, but I want a sequence, so a programmer-defined ordering, then I would use a list. If I want to be able to index quickly and insert reasonably quickly at the end, but not necessarily everywhere else, then I will use a vector. But all four of these types are ways of implementing the abstraction of a collection, a bunch of values that I'm storing. And both vector and list are ways of implementing the abstraction of a sequence, a bunch of values in a programmer-defined order. And for the rest of this course, we're going to be talking about ways of constructing our own abstractions and also using types and features of the language despite their encapsulation. So I'm going to demonstrate that we don't need to know exactly what this weird internal ordering is to be able to use unordered set effectively. Maybe we want to as a hobby, but we don't need to. All we need to do is understand how to use the operations of the unordered set or of the other standard collections themselves.